Okay, so we'll continue the modeling part. So when you apply unit loads, on the slab, then we can easily determine these are the unit loads that are applied on the slab. In addition to that, we get dead loads, and here it's a wind load. Modify. So wind load. Right. Okay. And so we get dead loads and the wind loads. Now, what we can do is we can apply the slabs that to represent the rigid diaphragm action that we get here. And if you look at the way that we have defined the slabs, the material, the slab concrete has been defined as a weightless material, but it has the mass. So once you apply the slab here, the mass will be properly represented, whereas the weight will be represented as 0. So mass is needed for calculating the dynamic properties. So here you can see we can apply the slabs, and the thickness of the slab has been selected at 175 millimeters. And on the plan view, I can actually apply all these slabs at once by selecting this particular option. And in addition to that, I can apply those slabs as well. So now all the slabs have been allocated. And you can see, although I have drawn at once, they are individual slabs. And so basically, the structure is ready. And if you want, we can apply the wind load as well. And here I will consider that the wind load does not vary, and actually the wind load varies with the height. But here I will consider that the wind load everywhere in the building is 1 kilonewton per meter squared, which is reasonably representative, but not 100% accurate, but reasonably representative. So what I do is I select here and apply the wind load. Wind in y direction, and the magnitude is the width of that side is 30 meters. 30 multiplied by floor to floor height of 3.6, so it is 108 kilonewtons. So wind in y direction. I can also apply wind in x direction. Wind in x direction, and the magnitude is 24 multiplied by 3.6, 86.4. So there are the wind loads also have been applied. In addition to that, you will get a load on the facade. So in addition to these loads, there can be a load on the facade, and there can be openings also. So I consider that facade will consist of something like a 200 millimeter thick wall, so that of density 20, and After allowing for openings, I'll consider height of 2.5 meters. So the facade load can be about 10 kilonewtons per meter length. Facade load can be 10 kilonewtons per meter load. So I can assign frame load, distributed, facade. I'll apply a load of 10. So now you can see facade. So whenever you apply a load, go to the graphics and see whether the load has been properly applied. So now the facade loads are there, the beam loads are there, and the core elements are there, the shear walls are there. So now what we can do is we can define the load combinations. And first thing is, what is the self weight of the slab? And you can see the self weight of the slab in this area is corresponding to 175 millimeter thickness. 0.175 into 24 is 4.2. Whereas in this area, I have considered a thickness of 200 millimeters for the slab. So we get 4.8. And then if you look at the finishers, I'm making an allowance of 1 kilonewton per meter squared everywhere for finishers. And services, I'm making an allowance of 0.5 kilonewtons per meter squared. And slab partitions and finishers and facade. Here you can see for partitions in all this area where the load is 1, the unit load 1, I'm considering a partition load of 1 kilonewton per meter squared for an office building having lightweight partitions. And in addition to that, I have also included the facade load also here in this combination. So with all that, in addition to that, you can see I have this live load. All these places, unit load 1, unit slab 1, 2.5 kilonewtons per meter square. That is the typical office load. Whereas in the lift lobby, I'm having a load of 4 kilonewtons per meter square. So those are the loads that have been applied. And because the loads are known, the support conditions are also established. Now I can save this. And then I'll save it as another name so that if you want to come back to this particular one, I'll be able to come back. And then what I can do is I'll go to 3D view. I'm going to create the 20-story building now so that we can do the foundations for that 20-story building. So display undeformed shape. What I do is I'll select all this and replicate once at 36 meters, that is 10 times 3.6 once. And then what I do is I'll select all the columns and then assign a smaller column from the 10th floor. So I'll go for a column size of 800 by 800 above that level. And then I can select all these and generate the structure, replicate at 3.6, 9 times. So the upper part of the structure is okay. I select this, replicate 9 times. So now the building is there, and we can, if you look at the 3D view, looks like that, and I can analyze the structure. And you can see, have a look at the natural period of vibration of the structure at 2.067, 1.911, 1.88. And if you want display, view, at the top, and then you can ask it to show the deformed shape, the model shapes, and say first mode. And if you want, second mode is a twisting mode. Third mode is moving that way. But now you can ask a question. Now, when we have this natural period of vibration of 2.06 for this 20-story building, is it realistic? Is it too low? And you will see that it's little too low because we have considered only the weight of the slab, but we are not considered the mass of the finishers and various other loads that can come onto it. So how can you correct that? What we do is we go there and define the mass source, and we say that it's coming all the way from elements and additional masses and loads, from elements and additional masses and loads. But we can see, how much load that we are going to allocate. So the facade, I'm going to say consider 50% of the facade load, because when I allocated the weight of the facade, I was little generous and I allocated 10 kilonewtons per meter, whereas the actual one may not be that high because the openings can be slightly bigger. So if I want, I can go for say 75% of the facade, modify. And then in addition to that, I have to consider the weight of finishers, services, and the partitions. So let's say, although I allocate 1 kilonewton per meter squared for finishers, the actual may be only about 0.6. And also the partitions I allocated 1, it can be about 1, about 0.75. So I get 0.6 plus 0.75. So altogether I get 1.35. And generally we can allocate about 30% of the live load also as being available. So which is 0.3 into 2.5. So once you add all those, you will get a value of 2.1. And modify. And then I can say, okay, now I can analyze the structure again and see what's the answer I get. So you can always adjust the masses and get a more realistic value. So I might get a very similar value. The reason may be that slightly higher now, 2.11 and 1.97 and 1.92, and so we'll just live with that. Those values looks reasonable, and sometimes the column sizes may be slightly bigger for this 20-story building. A more realistic size may be 900 by 900 columns and 700 by 700 columns. And we can also see what happens when we make that particular change. So we can say define section properties, because it's only a 20-story building. Frame sections can modify this to 900 by 900. And 0.9 and 0.9. Okay. An 800 by 800 column can be modified to 700 by 700 column. Now we can analyze this and see how it can affect the properties. So the columns have been made slightly smaller. And still it has not affected the natural period of vibration very much. And we see, so it has not affected the natural period of vibration very much. Sometimes when you change the section properties of the columns, can affect, modify. Yes, it's 0.9 by 0.9. I just wanted to double check whether I have made a mistake. 0.7 by 7, right? And what is this one? That is not relevant to us. That is not relevant to us because we are not used that particular section. And if I want, I can delete that property. Okay. Right. So these are the properties. And with that, we'll start looking at the foundation loads. So I can go to the foundation level now. And that's what we are interested in this particular exercise. So if I look at the foundation loads, I can say display, oh, sorry, before that I have to analyze the structure. I'll analyze the structure. I can ask it to display undeformed shape. And I can go and look at the foundation level. And I can ask it to display forces at the joints, envelope XY. And that is, first we consider envelope X with all the wind loads acting in X direction, envelope Y with all the wind loads acting in Y direction. Then envelope XI is, what will happen if out of all these different combinations, what is the most critical one? So envelope XY will give you the most critical case. And these are ultimate loads. And you can see the ultimate loads are in the range of 10,000, 9,300. And at one place you get 16,000 something. So here you get something like 16,000. And can one person tell what is the reason for the 16,000 kilonewtons at this particular location? And here you get another 11,000 kilonewtons. And here you get 6,700, 9,000, 10,000, around 10,000 here. But here we are having an additional column. But this particular joint, the support, the loads have gone up significantly. And can somebody tell what is the reason for that? And that is the presence of a concrete wall there. Because of the weight of that concrete wall, it has gone up. And in other places, you can see they are not excessive. Something like 3,000, 4,000, 8,000. So then we can also see the service conditions. So I can say service unit of XY. And you can see the values. Joint reactions 5,900. And if we look at ultimate, here you can see 5,000 will become 8,000. 2,000 something will become 3,000. Display. So service loads are in this range, which means, now we can see how by modeling the pile foundation, what will be the forces that will act on each pile. And in this particular case, when I model, it will be a reasonably regular foundation, but you can use the same techniques for irregular foundations as well. So any questions up to this point? So I'll go to third one. And now you can see the loads are something like 9,000, 8,000, that type of range. So the question is, what's the type of foundation that we'll use for this building? And because I'm planning to convert it to a 30-story building later, just for comparative purposes, I will go ahead with 4 piles under each column, though it may not be necessary everywhere, but I will use 4 piles of 1 meter diameter under each column, because 1 meter diameter pile can generally carry about 4,000 kilonewtons of load. 1.2 diameter piles can carry about 6,500 to 7,000, that range. Whereas 900 millimeter pile, you might have a maximum value of about 3,000, 300, 3,400. Sorry, not 3,000, about 4,000 kilonewtons. 900. 750 will have a maximum value of about something like 3,200, 3,300 kilonewtons. So in addition to all these values, we have to add the weight of the pile and pile cap as well. So one of the things we can do is we can simply model it and see what will happen with the foundation. So what I do is I will have a look at this particular flow, and we quickly create the pile foundation. And if you look at the arrangement, because I'm deliberately using 1 meter diameter 4 piles, which may not be necessary. And the usual rule is, when I'm using 1 meter diameter piles, the distance between centroids should be 3 times the diameters. So you get something like 3 meter for the pile to pile spacing, center to center spacing. And if I'm using 1 meter diameter piles, then they will get another 500 millimeter projecting out. So the center to center distance between pies will be 3 meters because we are having 1 meter diameter pipes. So you get another 150 to the edge of the pile cap and 4 piles like this, 3.5, 3.8 meters. So you get a pile cap of 3.8 meters by 3.8 meters by 3.8 meters. Not 3.8, 4.3 meters by 4.3 meters. So if I stop here and turn on the camera, here you'll see that we get a situation where, because I'm deliberately going for 4 piles, distance is 3,500 each on either side, 150. So altogether 4,300. So you get altogether you get 4,300 millimeters. So you get 3,000 and again 3,000 here, 500 here, 150 here. Likewise, you get the dimensions. So size of the pile cap will be 4.3 meters by 4.3 meters. So we can create one of the pile caps. So what I do is I select this. I'll draw a beam. And then what I do is I will replicate this at a distance of 2.15. X direction minus 2.15 and y direction also minus 2.15, and then I can replicate this at a distance of 0.65. And here you can see the coordinate is minus 2.15, half of 4.3, and this is minus 1.5. I can replicate this at 3, that at 0.65, so that all the boundaries are established. And then I can also see this minus 2.15, and I can draw this replicate that 0.65, and then three, and duplicate at point is 1.5, 2.15, 0.65. And then I can divide all at intersections and highlight that and get rid of that. And because I have all these locations, now I can actually create the pie cap. And to create the pie cap, I have defined a section earlier. Oh no, I have not defined a section. No, sorry. For the pie cap, I'm going to use the shell elements. And I can add a new section. That is pie cap. The center to center distance is 3 meters. So half of that is 1.5 meters. So I'll need a pie cap of at least 1800 millimeters. So I'm going to use 1.8 depth for the pile cap. And I can say pile cap concrete 30. And also in the same way, we'll define the pile as well. And the concrete is pile concrete 30. Diameter is 1 meter. We have to modify that. That is pile 1000. Right. So what we do is now we'll draw this pile cap. So if you look at this diagram, see now the pile cap has been created. And then what I do is I'll select these points and create the pile as well. Extrude. And then I will create the pile as well. Pile 1000 at minus 20. Let's say the length of the pile is 20 meters. We'll extrude and create those 4 piles. So I can see 4 piles have been created. Select all. And we can assign joint restraint as well. It's a temporary measure. So what I can do is and go to this level and rather than creating everywhere, I'll remove this support and the other files are here. So if you look at the 3D view of the diagram of the building, here you can see the file cap and all that has been created. And generally when we create the file cap like this, we'll divide the shell elements further. But for the time being, I'll keep them as they are, and then I'll analyze it. Display, cables, and if I want to go with service, I can go with service XY. Axial force, and here you will see that piles are carrying some axial load. And the magnitude of the axial load under service conditions will be 1528. And you can see what happens in the other places. So the loads are similar. So you can get the loads on the piles, and we can actually extend it further. And then we can also see at this level, we can ask it to display shells. And we'll go for the ultimate because file caps are designed for ultimate state. Y and the moment 1, 1. So you get a bending moment diagram indicating the stress distribution. And here you can see around the column, you get heavy bending moments. And the magnitude of the bending moment is 1400, something like that. In the pile cap that we designed also, we got a similar moment 1600, so you get 1400. But generally, we don't design for the bending moment just within the column. We just consider the bending moment just outside the column. So then we can ask it to display M22, that is the moment in the horizontal direction as well. So in that direction also you get a similar distribution. So we can extend this model further, and we can go to the level of applying the horizontal springs and finding the bending moments in piles and so on. So we'll continue all that next day onwards. Is that okay? Is Indranil still around?
Yes.
Indranil, what is the day you want to have the next lecture? Indranil?
Yes, sir. I'm checking the dates, sir.
Yes.
I guess, sir, we are okay with the 17th Saturday.
Okay, I will also get ready for that. If there's any problem, only we'll change it. Otherwise, we'll try and have it. Okay.
I will inform any changes we need.
Okay. Then.
So another thing, how many lectures remaining to complete this semester 3?
Maybe about 1 or 2 more. 17th and another day maybe.
Could better in the last lecture do some tutorial or some kind of that example kind of.
Okay, right. And also I will upload an assignment in 1 or 2 days time, right? And on the design of inverted T type foundation, right? So I'll do that also, and then we'll have 1 or 2 questions discussed. Okay, right.
Okay.
Then with that, shall I stop?